So, the idea is this. So, 7114 is ArcLink Part 2, this time in parametric instead of function mode. Let me pick up from where we started, which was, the question was, how do you find the length of a curve? And you remember the big idea of it. How do we do it? Not the formula for the integral, whatever, just big idea. How do you do it? Infinite triangles, okay? So in a finite way, you could say, I'm finding the distance between those points and that point and that point. That would be 3 estimating distances, and it would pretty closely follow the curve. And we could find those distances by using Pythagorean theorem, delta x, delta y here to get that distance 1. Delta x, delta y here to get distance 2. And delta x, delta y to get distance 3. Those straight side blues. And it would be a good estimate. And we could say, I suppose, if we wanted to get fancy math notation so we look smart to people, then he would say something like, it's the sum of delta x squared plus delta y squared. And in this case, it would be from 1 to 3. The more we did, the better fit we would get. And so, in terms of Riemann's sum, you could say the limit as the number of segments goes to infinity from 1 to n of that thing would start to approach an infinite sum, which we call an integral. And when we did that, anytime you do calculus and delta x gets infinitesimally small, delta x approaches the dx idea of a differential. What Leibniz called the smallest non-negative quantity for which you use mod. Okay? Now, that's great, but that's not really an integral to be worked with. There's no differential. I don't know what the limits of integration are or what even variable there would be. So the little notation work from there goes to remember that we said by differentials, which we studied just before we learned this, we know that dy dx is f prime. So dy is f prime dx, right? That said, we can then take this formula, leave dx squared by itself, but replace dy with f prime dx, quantity squared, and then do some algebra. What algebra can we do to clean it?
Pull out dx squared.
Yeah, there's a greatest common factor of dx squared. Once we pull that out, then square root it, it's just dx outside the root, and inside is 1 plus f prime of x quantity squared. Now, because x is the limit of integration, it's from x1 to x2 of the arc itself, right? Now, we could just as easily from here go to differentials in y and get a function of y and do it with y, and that's fine too, depending on the case. So far, so good. What you're really seeing here, you don't see it, but there are infinitesimally many little triangles here. And you're adding all of them, all those hypotheses to get a perfect arc length. Cool? Look then at a parametric case, which is the idea of the day. Parametric is cool because, for lots of reasons, but one reason is because it doesn't even have to be a function. I could do parametric and I could get some kind of crazy, hourglass shape or this kind of shape from here to here. Parametric can yield all sorts of cool paths. Right? All these different curves. But let's say we went here. Now, if this was created by x of t, y of t, remember parametric equations are x is a function of time and y is a function of time, I could still model or approximate the length by finding some segments. And then letting that number of segments grow without bound, and approximate it perfectly. Now, it's still the idea that it's the sum of many dx's and dy's. I'll pick up there. At that point, it's still the same. Now, here's where it starts to become a little different. This is a small distance of x. Now, I'm trying to get time into the mix here. Distance, as you learned in pre-algebra, is at its most basic level, rate times time, right? Now, the rate at which x is changing, how would you say that in calculus? The rate at which x is changing over time. The x dt. Could I also call that, in order to not confuse myself a little too much, can I also call it x prime? Okay. Now then, the distance is equal to rate of change in x, x with respect to time, rate of x change, times amount of time, a small amount of time. Yeah, so x prime dt. X prime dt. So this would then, this guy would become x prime dt quantity squared. Okay? That's rate times time. And then by the same token, y prime dt quantity squared gives you rate times time of y, and then yeah, dt squared gives you dt. So something like x prime squared plus y prime squared dt. What are the limits of integration in x, y, or t? T. They're t from time 1 to time 2, whatever that might be. So that's the idea on parametric arc-length. It's the same idea, multiple Pythagorean theorems added. So far, so good? Yeah. Cool. All right. This has to go pretty fast. All right, then. This has a mistake in it. Sorry about the typo. Where's the huge glaring typo you need to fix?
Y prime.
Yeah, it needs to be y prime here. Sorry about that. Y prime. Hey, it should be y prime. Okay, yes. I'm embarrassed. Yes, I apologize. Okay. So, would you use this idea on a really easy one? Find the arc length generated by those two parametric equations. You should not need a calculator. Okay, did you get to?
Yes.
Okay, easy enough. All right. Now, calculator, this can get a little sloppy. I'm a little behind on questions, so I imported quite a bit of calculator screen here, so you don't necessarily have to do this on your own. But had you been given this set of parametric equations and asked to find the length of the path, then the graph, you would put your calculator in parametric mode and graph it, because they asked for the graph. Now, in terms of what I would like to see, if the problem is not too terrible, then I think it's reasonable to expect in your work to show me your derivatives here, and then just use the calculator to evaluate the input. Okay. If, however, it was some nasty bunch, or if it was a multiple choice question where I didn't need to see your work, and you didn't feel like taking the derivatives, I guess you could just have the calculator, really that's estimating the derivatives, calculate the derivatives and evaluate, and you'll get the same thing, but either way, I'm good. If it's not too bad, though, on your homework, I'd like to see the derivatives. With me? All right, then. It's a pretty easy problem, so you don't need a ton of practice. There is one issue, and that's what the backside is about. It's actually two issues. I take it back. There's two issues. One's there, the other one I want you to add, okay? So this is always going to happen, that I get students confusing the two types of problem: linear movement versus rectilinear movement, okay, which is to say two-dimensional movement. So let me make clear one time in your head the difference here. If I give you linear movement, then the question might be something like the position of a particle moving along a number line is given by x equals 4 sine t. Okay? Find the distance the particle travels. The path, if I were to graph the path of the movement, then it would be along a number line. It would be something like, at time 0, where is the position? 0. And at time, over that time frame, does it always move forward, or does it sometimes move backward?
It moves backwards.
Why?
Well, if you just look at it, it starts at 0 and ends at 0 and doesn't stay at 0. So
Yeah.
it's going to go back. Also, its derivative is cosine.
Okay, yeah. In terms of how it moves, that's velocity. Its velocity is 4 cosine t. Now, over the time frame, 4 cosine t would be positive up to pi over 2 and negative pi over 2. And so the thing would move all the way out to 4 at time, I guess you could say at time pi over 2, and then it would move back here at time equal pi. And really those should be on top of each other because it's all along the number line. That's the path. Okay? So just look at that and tell me the distance.
8.
It's 8. Okay, 4 there, 4 back. It's 8. All right? Now then, if the problem is uglier, you could say, actually, I don't want to go there. What is not the path is to say, all right, here's the equation. I'm going to graph the equation, and here it is. And actually, I guess it's only 0 to pi, so a person would only say there. Okay? Now, this is not the path of movement. And so, what is not the distance is to find the arc length. Okay? People get the two problems confused, and I'll show you why they might do that in a second. But people say, okay, so I need to find the distance, so I'll find the arc length of 4 sine t, and boom, that's the distance. That is not the distance because that is not the movement. This is just how time and x relate to each other, but it is not how you moved. And so if I find the length of this path, I am not finding the distance. And I will get the wrong answer. Okay? Do not use arc length here. No arc length, or right. Arc length not equal to distance. Now when you do parametric graphs, you're showing the actual movement, where it was over time. So, for example, in 4 sine t, cosine t, can you tell me mentally what would that graph look like? If you graph, now you're not graphing x against time and y against time, you're graphing x what? It's a circle. Okay, perfect. It's what kind of dimensions? It's x squared plus y squared equals 16. Okay, so it's a circle with a radius of 4. Is it the whole circle? Not quite. So think about it for a second. Where does it start? Where does it end? Where does it start? 0, 4. Starts here. At pi over 2, where is it? 4, 0. And at pi, where is it? 0, negative 4. So it's going this way and stopping. All right. Now, this is the path. The graph is the path or the movement. So path length or arc length does equal distance. So if I want to know how far did the thing traveling along this path go, then I could do the arc length here and it would be. Okay? With me? Okay. The next gotcha is at the bottom. I screwed up in not teaching you this the first time just because basically it's really Saxon's fault. So you might have been having a few arc length problems in the last few problem sets. And I should have warned you about this ahead of time. But again, it's supposed to be a topic you have seen before you do this lesson, but it's not. You got it over. So here we go. I think in set 112, you had something like x to the 2/3, which it doesn't matter if you don't know the graph of that, but it's a Siegel function, on -8 to 8. And you were asked for the arc length, okay? Now, the arc length then would be, because this is not parametric, it's normal, it's more like 1 plus f prime squared. So it's square rooted. So 1 plus 2/3 x to the -1/3 quantity squared dx from -8 to 8. Okay? Now, if you put this in your calculator, you might have had a problem. It might have said, hey, you dummy, or no, I can't do that, or something like that. Get it? Some people. Okay. Why? Yeah. This here is 2 over 3 cube roots of x. And that, when it hits 0 in there, it's going to have a little bit of a problem. It's going to say, whoa, 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 you're dividing by 0. Okay? Now, that's a problem. When a function, or when the integrand isn't continuous over the interval, you have what's called an improper integral. Now, this is actually a huge idea of this class, which we'll come to in about set 127, 128. But think for a second, just to talk about it. What if I asked you to calculate this integral? Okay. Now, graphically, so what? What's the problem?
Vertical asymptote.
Yeah, there's a vertical asymptote at 0. It's not defined there. Analytically, why is that going to yield a problem? Yeah, that's not so much, okay? So, put yourself in the shoes of math 300-400 years ago. But now you know calculus, especially limits. How could you work around that? 0 is a problem, right? So let's not use 0, let's use a and see what happens as a moves closer to 0. So this would actually be done by saying, let the starting point be a and move a close to 0. Now that is the improper integral idea. Even more fun would be if instead of going to 3, you let it go to infinity. In which case, you let this be b, and you say, what happens as b goes to infinity? Yeah. Actually, you don't really do that. You do 2 integrals. That's bad math. Nobody would ever do that. You would. Yeah, it's cool. You would actually introduce some middle number, call it 4, and go one integral from a to 4 and one integral from 4 to b. You don't do that like that. It looks, yeah, it doesn't look like you're right. Okay, that's how you should do it. You will do it. All right, but that said, don't sway. Let's go back to the actual idea for now that you're going to need to understand. Your calculator will not allow you to do that. So instead, you're kind of going to use that limit idea. You're going to say, I have a discontinuity at x equals 0. So you break it up into 2. You're going to let this integral be from -8 to almost 0, but just below 0. So maybe -0.000001 of the root thing, and then add what? The record. 0.000001 to 8. Now, this problem was actually even. You could prove that. And so because it's even, here you could actually do something else besides two integrals. What else? Yeah, you could just find one and double. And that works fine. If you're not sure it's even, or, then you can, this works every time. Okay? Say then you looked at a parametric arc length problem. Say you have this, which I don't even know what the graph looks like, but I don't really care. And you wanted the arc length. The setup would be from where to where, or from when rather to when. -8 to 8, parametric arc length by way of review is x prime squared. Okay, so what's x prime? 1/3 t minus 1 to the -2/3, that quantity squared, plus 2/3 t to the -1/3 quantity squared dt. Now you will, over the course of the semester, it'll start to be habit. I got to check for continuity. I got to check for continuity. Is this continuous over that interval? How many discontinuities? 2. Where? Yeah, 0 and 1. So if you were to break this into pieces, you'd have to go 1 from -8 to -0.000 whatever 1 of the root thing plus positive point, from 001 to not 1, just below 1 of that thing plus just above 1 to 8. Okay. Now, if you were to do this more analytically without a calculator, then you would have limits there and let those numbers put everything in your approach. Okay, that's the lesson. Are you with me?
No, I'm against you.
What do you mean? No. Oh, okay.
It's just really annoying to type that.
I agree. You should be grateful you have a calculator that does it for you at all. Yes. This one?
Yeah. I almost have I was trying to describe something that happened on Monday and I said, a few weeks ago. Oh my God.
It does seem long. I agree. All right. Homework 112, 113. Here's the replacement answers for 112 in red and 113 in black. I will be happy to take any questions. Just say whatever. 12.
Can we also go?
12 this or 13 that. You don't have the packet?
Oh, I don't know how
Didn't I give you packets for this semester? Or these?
Yeah. Yeah, it was like yellow. I'll find it.
Okay, 12 this or 13 that?
112, number 4.
4.
Only part. Only parts. Oh, I knew.
Only part?
Only, I don't remember. I knew part C, but I know what part.
Oh.
And then also 22 and
On 12 and 13.
on 12.
12, 22,
And 23.
12, 23.
25.
12, 25? Okay.
And 21.
12, 21.
Are we just doing 12?
No, give me whatever you got.
Oh my goodness.
There's one thing, 12, like, 12 was the problem with the stuff that we just did. He wants to do that.
18.
It was ARC one?
Yeah, it was.
But it was regular.
Oh, was it ARC, was it Seek and Q?
Oh, no, it wasn't Secret Cube. If you look at the project,
You can use your, so yes, do it now you can do it. So yeah, go ahead. Okay, 13, 12, whatever else? 12, 15?
Oh,
They're
no,
both-
like 13.
13,
13, 12, 13, 15, 13.
13, 12, 13, 15, 13.
Yeah, I'm good on 12.
Okay. Did you say 18 at the end?
Yeah.
Okay. Shall we begin? 12.4. Is 12.4 a question?
Yeah. I just need part C.
12.4c. X equals 3. Okay.
Oh, yeah. Row. No, I just need to put the DY.
Okay. Gotcha. So, in part C, dy dx, find dy dx both ways. Verify they're the same. Okay. So, if you do dy dx parametrically, then we do that by saying what's dy d theta, dx d theta. Leaving? dy d theta is 4 cosine theta, and dx d theta is negative 3 sine theta. Cool. Okay, now here's where I can help you out a little bit. Dy dx in rectangular is, can you just tell me what that is when you did the implicit? Dy dx is?
72 minus x over y.
Really?
Maybe I did it wrong.
No, you might be right. I don't know. Let me see. Not to distrust you, but to just do dy dx.
Oh my god, maybe I did it wrong.
Negative 2x over 9 times 16 over 2y. I get something like negative 16x over 9y.
Never mind, I forgot that it wasn't this simple.
Okay. Do you agree with that derivative rectangularly? Okay. Now let me show you then. The goal is to show they're the same. So we need to take one form to the other somehow. Most people like to sub for x and y because they're there. So if you were to do this, dy dx then is negative 16, and in place of x I could say it's 3 cosine theta. In place of y I could put 4 sine theta. This then is negative 4 cosine theta over 3 sine theta, which is, okay. So it might look something like that. You don't necessarily have to go both rectangular or polar. You can go either way. Okay. Can I go to 1222? 1222. Yeah, hook yourself up. Does anybody have a question on 1222 still?
Yeah.
Okay. Strangers in the night. Integration by parts or use of? I guess you could do integration by parts, but isn't use of right there? Yeah. Okay. So let's use of. What do you say? Actual use of or just mental use of? Do you even know what I'm talking about? Okay, this is natural log of u, straight up. How do you integrate natural log of u? So I guess you are going to have to use integration by parts. Even if you use some first, you're still going to need integration by parts. So is it better just to integration by parts to start with?
Why can't you just do
You can, but when you use sub, it's this. Now, if you, I just assume people have that memorized.
Yeah, I was like, don't we know what that is?
Yeah, many people know that that's x natural log of x minus x.
Oh.
X natural log, actually u natural log of u minus u.
Oh, that's the thing that I just don't.
What do you do with that?
That comes from integration by parts. So easiest, least time kind of thing. That's how my thought process would go. This is like the integral of natural log, which is like integration by parts. With those ideas then, this then is, what is u in this case?
X squared.
X squared. So u natural log of u is x squared natural log of x squared minus x squared, and not plus c, but from root e to e. Now, that's fine, but if you'd rather show integration by parts, I can do it that way. Would you prefer to just do it that way?
Yeah, I did.
Or is this okay?
This is okay. Well, you don't have to change the value if you change it back.
See, that's why I didn't do use sub and all that stuff, so I didn't have to mess with things.
You know, like.
If on a definite integral, I can,
Other-
if I cannot do that, that way.
Like,
Okay. Okay. 23? Is 23 a question still?
yeah.
Okay. 23 is 0 to 1. 0 to 1. I haven't done this one yet. 0 to 1. Cosine. Okay, so I can imagine a couple sticky places here. One is that in terms of u sub, we can really go either direction, right? The fact that none of those choices have a negative in them, to me, feels like they let you, because no negatives in the choices, I feel like u was probably sine, not cosine. Because if you had been cosine, then I probably would have seen a negative, but I could be thinking about that wrong. Are you with me? Okay, so if that's the case, then du is something like cosine pi x over 2 dx, which means, chain rule, sorry, times pi over 2 dx, right? So cosine pi x over 2 dx is like 2 over pi du. If I solve for what I actually have, then I need to move that over there, yeah? So this then becomes u 2 over pi du, and then the limits. If, man, I hope I chose right. Now I'm thinking I could have gone either way, and my answer's not going to be there. Darn it. If I go 0 there, then u of 0, or sine of 0 is 0. Uh-oh. And 1 is sine of pi over 2, which is 1. Is that there?
Yeah. Yeah.
Yay! Does cosine get you the same thing? Come to think of it, I think it might be also the same. You have a negative, but you get another negative somewhere else. I think either way it's good. Okay, are we cool? 1225. Prove. Okay, now the danger here is making a simple problem complicated. On the most basic level, do you understand why this is, not indeterminate? Small numbers times themselves many times. That's not, I wonder how it'll come out. If I multiply a 10 times itself a billion times, that's approaching 0, period. You know what I mean?
Yeah.
That's not an I don't know. That's a I know. It's 0. Okay? However, that's not a very proofy kind of thing. So the question really amounts to use formal math to prove this is not indeterminate that it is always equal to 0. Okay, now a harder point would be if they didn't give you any help. If they just said, many books do this, say, prove 0 to the infinity is not indeterminate. It's really hard to just get started there, but they're helping you. You're really trying to prove that if you have some case of a limit of two functions that went to 0 to the infinity, that it's not indeterminate using our normal process for exponential indeterminate forms, okay? So we're going to use the limit of indeterminate forms work we usually do. We normally do e to the limit as x goes to a of natural log of x, f of x to the g of x, okay? I did not change that product. That's still mathematically sound. It's still the same. If I then do what I normally do, which is to bring down, okay? Now, normally I would make that a quotient, but let's pause here and see if I can tell what this is. G of x goes to what? Based on, sorry, say it again? Okay, so go based on their directions. They said create a f to g that goes to 0 to the infinity. Now that then implies that g is going to infinity. And that means f must be the part that's going to 0. Okay, so then building out to what we have here, g is fine. What is natural log of f then, assuming this is from the positive side? What is natural log of f approaching? Negative infinity. Now if you put those two together, infinity times negative infinity, is that, I don't know? That's negative infinity. Okay, so it's e to the negative infinity, which is most definitely always 0. Okay? Okay, so that's the idea. 1221? Is that the replacement?
I don't know. I don't know.
Okay. Oh, I told you what to use, darn it. Oh, this was 7112. No wonder I told you. Okay, so x equals 5 sine theta. So, all right. So remember, you're not just subbing in the squares, you're subbing everywhere. So x squared is 25 sine squared. Dx is 5 cosine theta. Okay, so far so good. Clean up. This is 25 factored out, and 1 minus sine squared is cosine squared. Okay, doing a little more cleanup. You got a 5 here, a 5 here, a 5 there. These all divide away. And it looks like you're getting something like cosine squared over sine squared, or cotangent squared. Okay, do you agree? Do you see where I'm coming from?
Yeah.
Okay. So how do you anti-differentiate cotangent squared? What do I do next? Okay, so that's not a clean antiderivative, but if you use an identity, you'll get a clean. What's cotangent squared? Cosecant squared minus 1. That helps you because cosecant squared is a clean derivative, or sort of. What is it the derivative of? Yeah, negative cotangent minus theta plus c. Then you draw your triangle, so I continue, or do you get it from there? Drawing the triangle and subbing back? Continue or no, you're good?
Oh my god, never mind.
Bye. You're welcome, thank you. I'm sorry, I didn't hear you. Are you good?
Well, summing back, they kept one draws triangle.
Okay, so I take this as...
Oh, wait, no, I see.
You got it?
Yeah.
Okay, cool. Okay, 13, 12.
Okay, I don't understand how you got it. I got.
You go over there.
Oh,
Wait, 19 starts a lesson. 19 is the lesson of the.
is that the secant cube?
Yeah.
You can skip that one.
Oh.
Okay, the results of secant cube, which we had done. Okay, so 12 now, yeah?
How did you get it? Like, I just got, like, added plus.
Is that the replacement?
Yeah.
Yeah.
Oh, okay.
So how could you multiply?
I don't have the original problem. I have my first step, which is to get x's on one side, y's on the other. Can I pick up here?
Good.
Okay.
Yeah.
Okay, cool. So the antiderivative of this side is, okay, I think you can see then why, if you forgot the natural law or the absolute value, you're going to be in trouble because that in this condition. Yeah, so make sure you have absolute value.
Yeah.
Okay, over here, what's the antiderivative?
1/2.
Could I leave that absolute value off that? Yeah, it's positive, so it's fine. Okay, let's see, yes, thank you, that's crucial. Okay, use the initial now or use it later? Now, okay, so if I use it now, I get the natural log of the absolute value of negative 2e equals 1/2 log of 1 plus c. Natural log of 1 is 0, so c is the natural log of negative, the absolute value of negative 2e. Cool?
Yeah.
I guess you could say it's the natural log of 2e if you just use the natural, whatever. Do you clean that up or do you just leave it like that?
Wait, well,
Negative, absolute value of negative is just natural log of 2e, right? So you could just say,
yeah. How did the other side get to down to just C?
natural log of 1 is 0. Yeah. Okay? Okay, are we fine so far?
Yeah.
All right. So going back to where we're at, natural log of the absolute value of y is 1/2 log of x squared plus 1. The absolute value is not really necessary because it's positive, plus the natural log of 2e. All right, now, I didn't say it in there, but I think you probably knew it, or at least you can tell from my answer. I want you to solve for y as a function. Find a single function of y through that. Okay, so solving for y now. What do you do first? Okay, so here's a huge source of error. Maybe it's your error. When I exponentiate, can I e here, e there, e everywhere?
No.
Why not?
Because that's stupid.
Because that's stupid. Exactly. It's like if you said this, and you say, "Hey, I feel like squaring, so I'm going to square here, square there, everywhere." Is that true anymore? No. Okay. So when you do something, you do it to the whole side. It must be something like that. And so when you exponentiate, you shall not do it like that, but the whole side, not term by term, which is a very common error. All right. So the other side is, the left side is cool. It's the absolute value of y. The absolute value does not just go away because you wish it did. Okay, it's still there. How about this? Does this e there, and knock out? Do these cancel? They do not. You have to make it a single logarithm, so it's e to the natural log of, combine all that log rules. Square root of x squared plus 1 times 2e. Yeah? All right. Now, e to a log, those are inverses. So the absolute value of y equals the square root of x squared plus 1 times the quantity 2e, which I should probably put up front. Okay, now what? Plus or minus. If I leave it plus or minus, is it really a function that yields a value for any x? It is not. So I need to choose. How do I choose? Yeah, you go based on the point. In order to make z 0, negative 2e, what has to be out there? A 0 or a positive or a negative?
Negative.
It has to be. Okay. Does that make sense?
Yeah.
Okay, 13, 15. Is that still a question? Yes, it is. Can you, first of all, make sure your calculator is in degrees? Yeah, that is not good. Go to your physics part of your calculator, whatever you're going to do. You most definitely do not add in polar. You cannot add polar. You have to convert it to components. How much horizontal vertical here, how much horizontal vertical there, and combine. So the total I hat is negative 4 cosine 150 plus 6 cosine negative 200. Okay? You could actually, I guess, if you wanted to do I hat, fine. If you wanted to do component form, that's fine. That's horizontal. The vertical is the same, but with sine. Negative 4 sine 150 plus 6 sine negative 200. Those are breaking those hypotenuse vectors into horizontal and vertical components and then adding the two components. So far, so good?
Yeah.
Okay. If you are to store this to I, store this to J, that would be peachy. I hope I'm not telling you that too late and you already don't have I. All right, it does say answer in polar form. So, do you have numbers for me? Just so I have something. Anybody?
Negative 2.174 I hat
Okay.
and 0.05.
J hat. Okay. So the sum of those two forces is something that goes left 2 units and up 1 unit. So this is the sum vector, but or the resultant vector, in component form. How do you put this now into polar form? How do you do the magnitude or the hypotenuse? Pythagorean theorem. Yeah. So this would be something like that I hat squared plus the j hat squared square rooted. How do you do the angle? How would you find the triangle angle? Inverse tangent. Now be careful with the sides here. You don't want to get a negative in there. It'll kook you out. So I would, if you have a negative in there, figure out how to deal with it. But I would just do inverse tangent of the positive versions of j hat over I hat. That gives you this angle. How do you then find the polar angle? Which, yeah, if you're going degrees, it would be 180 minus that result, and if you're going radians, it's pi minus that result. I guess you're in degree mode now, yeah, so I guess we'll go 180 minus inverse tangent of the absolute value of j hat over I hat. Again, it's important that you have that absolute value there, because if it's a negative, inverse tangent of a negative is going to give you an angle of this quadrant here, and you don't want that. Okay? Okay, boom. 18. Question on 18. Boom. Approximate the length of the curve y equals 4 to the absolute value of x. Do you remember what absolute value on the x does? Okay, so don't memorize, conceptualize. Forget absolute value when it's on the function, it does this on the function. Instead, the big idea is the absolute value does nothing to positives and changes negatives. So here's y equals 4 to the x. It does nothing to the positives. So this side stays the same because positive x's are unchanged. It makes negatives behave like positives. So these places where this wanted to, they're not going to happen because now these negative x's are going to be like positive x's, it'll be more like that. Now then, to do this kind of, what is this area or length?
The negative x's for positive and it's
Say it again.
like, how did you just say the negative part?
This, yeah. So these points, that never happens. Because when you put in a -2, it gets made a +2. And then you're going to get an outcome of 4 to the +2. So on the negative side, it's actually going to behave just like the positive side. So that this side is going to be a reflection of the positive. Okay, so the length of the curve, you probably have to do 2 different intervals. Like we often have to do piecewise, right? So for this piece is like, more like instead of y equals 4 to the x, it's more like y equals 4 to the -x. Because it's taking the opposite of those negative x's. You with me? And this part is y equals 4 to the normal x, because positive x's are unchanged. And so then you work out the arc length thing from -2 to 0. 1 plus, I don't remember how to take the derivative of exponentials anymore, although I taught it just this morning. It's x, there's a natural log in there somewhere. Anybody remember?
It's something over ln.
Oh, for
For
x.
The
example.
natural log of the base, isn't it, right?
Yeah.
Over x ln.
Times, and with the negative because of the exponential, right? So something like
Sorry.
this.
Wait, how would you do it because there's 2 equations?
You're going to have to do 2 intervals. Is this feeling good?
Sure.
I say maybe. Okay. And then from 0 to 4 of 1 plus, and then the derivative of, now this is just normal 4 to the x, so that would be more like natural log of 4 times 4. It's not undefined there, right? 4 to the 0 is fine. It's not.
Oh, yeah.
That's good that you remember that.
Okay.
I like-
Okay.
Do you remember the answer?
5?
Oh, I do.
I don't know.
I do. Wait, it's
That's actually probably,
270.434 units.
which actually makes sense.
Oh,
because-
you were really close.
Yeah, it just occurred to me, 4 to the 4th is like 64. That's way up there. So yeah, that's, I don't know.
Okay, this perspective. So I solved for y.
So much to do.
But I got that. So how?
You got that for C? Isn't that
Yeah.
what I got?
Well, how do you do that? Like, put it back
Oh,
in
but
office. 'Cause-
Oh, you stop later.